we talked about mean value theorem. Mean value theorem, if I can write it without moving my screen, for differentiation a long time ago. And if you remember we were given a function, we were given some function, and the function was continuous on a closed interval from a to b, and it was differentiable on an open interval a to b. And we said there was a point within, in between a and b, such that the slope of the tangent line at some point c between a and b is equal to the slope of the secant line, or the average rate of change from a to b. Another way to think about it, there is a tangent line between a and b that is parallel to the secant line going through a f of a and b f of b. And how we wrote it was like this. There existed point C such that f of b minus f of a divided by b minus a, this is slope of secant line or average rate of change, was equal to instantaneous rate of change, definition of derivative. So there exists C within open interval AB such that our slope of secant line was equal to our slope of tangent line. And this was for differentiation. Now I want to show you the equivalent theorem for integration. So let's go down and write mean value theorem. But in this case, it's going to be for integration. And what is it, you may ask? Let me start with this. Let's say you are given a function. Any function. So let's say function is going like this. But you know the function is continuous from a to b on closed interval ab, and because it's continuous, you know it's not gonna do things like this. It's not gonna jump up and down. It's not gonna have any asymptotes or things like that. So you know it is continuous, which is in our case on the AP test usually the case, which is nice. And let me ask you this. Let's say you pick any point between a and b. You can pick a if you want to, and you're going to draw a rectangle with the height of our function evaluated at the point and our width of b minus a, or between a and b. So in this case, if you pick the point a, our rectangle is going to look like this. If you pick point right here, our rectangle is going to look like this. If you pick, now let me erase all this. If you pick the point to be right here, you're going to go up, and that's going to be our height, and your rectangle is going to look like this. If you pick, I think you get the point. If you pick this point, you go up, draw the height, and our rectangle is going to look like this. Now let me ask you this question. You know the area under the curve from a to b is integral from a to b of f of x dx, given the function is non-negative. And let's say you pick our point A to be the specific point, and let's compare the area of this rectangle with the area under the curve. Is this larger than the area under the curve? In this case, yes, it is. If you have picked the point B, to make the rectangle, your rectangle is going to look like this. And let me ask you, is this area larger or smaller than the actual area under the curve? And in this case, it's smaller. And let me ask you this. Can you pick a point C such that if you draw the rectangle, the area of this rectangle is going to be equal to? And how do you write this? Our height is f of c, and our width is b minus a. Can you find a point C in between a and b such that our integral from a to b of f of x dx, or the area under the curve, is equal to area of this special rectangle? And mean value theorem for integration says yes, you can. And there exists C, so this is another existence theorem. There exists C within, in this case, it's closed interval from a to b, such that our integral is equal to f of c times b minus a. And you may say, how is this even related to mean value theorem for differentiation? For differentiation, this thing is telling you there is an instantaneous rate of change that's going to equal the average rate of change. But mean value theorem is telling you there is a point where you can make a rectangle such that area of a rectangle is equal to area under the curve. How are they even related? And fundamental theorem tells you how they are related. They are exactly the same thing. And why? let me ask you this. Why? Let's define our function capital F of x such that when you differentiate capital F of x, you get f of x. So all I'm telling you is f of x, capital F of x, is antiderivative of f of x. If you differentiate capital F, you get lowercase f. Now let's write mean value theorem for differentiation. Mean value theorem for differentiation tells you there is point C such that f of b minus f of a over b minus a is equal to the derivative of capital F at some point C, and derivative of capital F is lowercase f, so lowercase f at some value C. Now, what's f of b minus f of a? By fundamental theorem of calculus, change in antiderivative from a to b, or capital F at b minus f at capital F at a, is integral for a to b of lowercase f dx. So you know this thing is equal to integral for a to b of f of x dx, and multiplying by b minus a gets you exactly what I stated above. So in fact, mean value theorem for integration and differentiation are the same thing. Now let's try one example. Let's say y is equal to x squared, and you're given interval from 0 to 2, and you want to find value c that satisfies the mean value theorem for integration. So what we want to find, the x squared goes like this, and this is 2. You want to find value c such that if you get the area of a rectangle, it's going to equal the area of the curve, that's going like this. So let's try it out. We want to find our value c such that integral from a to b, and in this case a is 0, b is 2, of x squared dx is equal to our function evaluated as c, or c squared, times the width of the interval, or 2. So c squared times 2 minus 0, or 2. And integral from 0 to 2 of x squared dx is x cubed over 3 evaluated from 0 to 2. And this thing is equal to 2 cubed is 8, and 0 cubed is 0. So minus 0 is, you don't have to write it out, is equal to 2c squared. So c squared is equal to 4/3, or c is equal to plus or minus square root of 4 is 2 square root of 3. And are we going to use plus value or minus value? Well, you're looking at it from 0 to 2, so only positive value is what you care about. So positive 2 over square root of 3 is the value of c that meets the requirement. And one last thing I want to mention before I close this. Is there a systematic way of finding value of c? What I'm saying, evaluating this integral takes some time. An integral of x dx obviously doesn't take too much time, but there are some integrals, such as integral of sine of x squared dx, that's impossible to evaluate using elementary function. Using elementary function, you cannot find exact value of sine of x squared, or integral of sine of x squared. You can approximate using Taylor series, as we're gonna do in calculus BC video later on, but you cannot find exact value of this. So what you may ask is, if there's a way to systematically find the value of c, maybe there is an easier way to evaluate the area under the curve. But it turns out finding value c is there's no systematic way, or there's no easy way of doing it. So that's not the way to go when you're finding area under the curve. But when given a question of finding c that meets the requirement for mean value theorem, you should find the area under the curve and use that value to find c.